Monsieur l'administrateur, mes chers collègues, mesdames, messieurs, c'est un grand honneur pour moi de me trouver aujourd'hui au Collège de France comme titulaire de la Chaire Internationale. Bien qu'elle ait été courte, je garde un excellent souvenir de mes 2 visites antérieures à cette institution, qui peut à juste titre se vanter de 5 siècles d'excellence académique. C'est de tout mon cœur que je remercie l'Assemblée des professeurs du Collège de France qui m'a élu et le Collège lui-même pour l'accueil qui m'a été réservé ici. J'attends cette année des contacts féconds et des travaux scientifiques réussis. À titre personnel, je voudrais aussi remercier le professeur Jean-Claude Pecker de l'intérêt qu'il apporte à ma visite et de notre collaboration dans le domaine de la cosmologie. Et puisque la cosmologie est mon domaine de recherche depuis 4 décennies, c'est un aperçu de ce domaine que sera tout naturellement consacré cette leçon inaugurale. Je suis bien conscient de ce que mon intervention pourrait vous donner une pauvre illustration de votre élégante langue parlée sans élégance. Et je vous demande à l'avance de bien vouloir m'en excuser. Je tiens à remercier l'Alliance française de Pune de m'avoir initié à la langue française, mais j'assume la pleine responsabilité de mon accent indien. Il est hors de question que je veuille vous imposer la totalité de cette leçon dans un français si hésitant. Aussi ai-je demandé à notre administrateur et l'ai-je obtenu l'autorisation de ne présenter en français que la seule introduction de ma leçon. La cosmologie, c'est la branche de l'astronomie qui concerne la structure à grande échelle de l'univers et la problématique de son origine et de son évolution. À mesure que l'homme améliorait sa capacité à regarder le cosmos et que parallèlement son raisonnement, étayé par des faits scientifiques, pouvait aussi progresser, le domaine de la cosmologie a subi une évolution profonde. D'abord, exercice spéculatif et philosophique, la cosmologie est devenue une entreprise scientifique dans laquelle la découverte de faits d'une part et d'autre part l'élaboration des théories se sont développées de pair. Aujourd'hui, la cosmologie jouit d'un grand prestige. Elle semble être devenue la branche la plus séduisante de l'astronomie. Bien sûr, de nos jours, la panoplie de télescopes et de détecteurs fournis par la technologie justifie l'audace des théoriciens. Mais toute cette audace, propre à la formulation théorique, doit être étayée par des faits. La cosmologie est-elle aujourd'hui réellement ancrée sur des faits avérés ou reste-t-elle spéculative? Répond-elle aux exigences de la méthode scientifique? Et satisfait-elle notamment à l'exigence de proposer des vérifications reproductibles? C'est à ces questions que je tâcherai de répondre, tout en gardant comme arrière-plan de mon discours une vue perspective sur l'évolution de ce domaine. je reconnais bien volontiers que certains des experts ici présents pourraient se convaincre que mes opinions s'éloignent du courant de pensée dominant. Si je trouve néanmoins le courage de m'exprimer, c'est bien parce que le Collège de France, fondé par le roi François Ier, a toujours lutté contre tous les dogmatismes. La statue de Guillaume Budet, l'éminent humaniste, se dresse ici, toute proche de la devise Docet omnia. C'est avec ces remarques que je termine mon introduction et que je commence mon exposé en anglais. Le résumé en français a été remis à l'entrée de cette salle. Ladies and gentlemen, I am going to talk about facts and speculations in cosmology. And before I come to the subject, I want to make a general statement which I have written here. Facts and speculations are both essential for a healthy growth of science. Facts tell us all that we know to be true about the universe and make up our current experience. Speculations allow the human mind to break out of the confines of current experience and to think of scenarios that may appear quite strange. However, all such speculations must ultimately be checked against facts if they are to form part of science. So, this is how I like to see science evolve as a subject. So, against this background, this is the kind of opening thesis I make. The question I want to pose, that is cosmology as practiced today a science? This is the question I want to come to eventually. So, I want to start with ancient cosmologies, just to give some example. In ancient cosmologies, I have one from my part of the country, what we call Brahmanda in Hindu mythology, Hindu cosmology. It is a big egg, cosmic egg, that is supposed to contain the whole universe. So, here the artist has opened out the egg to show the whole universe has come out. So, this was one idea that people had. Another from a different part of the world is the Norse world tree, Nordic civilizations. They thought of the universe as being carried on the branches of a world tree. So, not only branches, but also the roots. So, it was the whole tree which was carrying the universe. Well, we can say that concepts like these are today treated as highly imaginative speculations and no more, because they did not have any support in facts. We don't find a big egg, or nor do we find a tree which can hold everything. So, we can ask, how do we check whether the theory is along the right tracks, that it is proceeding in the right direction. So, there are some symptoms, some signs you get that things are not going quite right. So, we should change. Now, one example I want to give is the Pythagorean concept of counter earth, an idea which was like this. You have the sun here at the corner, but there was a central fire around which the earth was supposed to move. That was their belief. It was not moving around the sun. So, people started asking them, why don't we see the central fire? So, the answer was that because there is a counter earth which goes around the central fire, which exactly blocks your view of the central fire. it had to be invented because otherwise the theory would be disproved. So, then people started asking, why do not we see the counter earth? So, since the idea originated in Greece, they said Greece is facing in the other direction. So, you do not see it. However, people tested the idea, they went around and they found nothing there. So, the idea died a natural death. So, here I want to give this as an example of when you have a scientific theory does not work or has conflict with facts, you invent some extra assumption to keep it going, but then it goes on building up extra assumptions and they do not ultimately work out. An example of this was the Greek epicyclic theory. The Greeks believed everything moves in circles. So, and since the earth had to be fixed, the planet should move in a circle around the earth. That was the Aristotelian concept, but that did not seem to work out. So, they put a second circle. So, the second circle is here and the planet is moving on this, and the center of this circle moves on the bigger circle. So, they thought with these two circles they will be able to explain. Of course, the orbit becomes more complicated as you see. When this did not seem to work, they put a third circle and so on. So, these circles became known as epicycles, and you could attain the desired accuracy for a while by having a certain number of epicycles, but then it did not seem to work right. So, it meant you were on the wrong track. Another point, now this epicyclic theory was believed by the majority, but it turned out to be wrong. I want to give you a relatively recent example of where a majority view is not necessarily right. I want to go back nearly 100 years. This is a extract from a popular book written by Agnes Clerk, whose books were very popular on astronomy, very well read. It is called A System of the Stars. Before I come to this statement, I want to tell you what the issue was. Astronomers were discovering, apart from stars, bright nebulae. Nebulae were cloud-like objects which had light diffuse spread out rather than concentrated like a star. And the question was where these nebulae were located. And the majority felt that all the nebulae that you see are part of our great Milky Way system of our galaxy. That was the belief that majority had. There was a minority which felt that this particular nebula, which was called the Andromeda Nebula, is, for example, not part of our galaxy, but is very far away and is a galaxy in its own right. So, this was the controversy which was building up around the time she wrote. What did she write? The question whether nebulae are external galaxies hardly any longer needs discussion. No competent thinker with the whole of the available evidence before him can now, it is safe to say, maintain any single nebula to be a star system of coordinate rank with the Milky Way. In other words, she is dismissing the minority view that this kind of system could be a galaxy in its own right. So, this she said in 1905. Within 20 years, people realized that there are galaxies, and Andromeda is one of the galaxies which actually is same rank, similar to our Milky Way galaxy. So, let me come now to situations which are on the positive side, where speculations have worked and they have been supported by facts. I want to give example of Newton's law of gravitation, which explained the law which Kepler had found for orbits of planets. Now, Kepler discovered that there are, in fact, he went away from the epicyclic theory of planets, and he found that planets move in elliptical orbits in such a way that if you take the sun which is at its focus, then the line joining the sun to the planet sweeps out equal areas in equal intervals of time. This was his observational deduction by observing planets. And Newton's law of gravitation was able to mathematically explain why this is so. So, if you come to what Newton was after, Newton's law was not just for explaining Kepler's motions of planets, but it was a universal law, and this picture symbolizes this. He is looking at the moon and the apple is about to fall on his head. The idea was that both the apple and the moon are being attracted by the earth's gravity. So, it is the same law which is applying not only on the apple, but also on the moon. And this is a big speculation to go from the apple to the moon, but it seemed to work. And not only seemed to work, it worked well in several different contexts. I just want to briefly enumerate. One is the so called cometary motion. Here you have the Halley's, the comet which became known as Halley's comet, shown on the Bayeux tapestry. This was around 1066. Now, Edmund Halley found that there was a comet coming near the earth every 75-76 years, and his idea was that there were not different comets, but the same comet was coming again and again, and he therefore made a prediction when the next comet would come. And since Halley was somewhere in the 1680s that he made this prediction, his prediction was borne out, and here is the picture of people in London observing the comet when it actually came exactly as predicted by Halley. So, here was an example of a mathematical theory which really quantified a speculation working out as per facts. Another mathematical exercise which turned out to be factually right based on Newton's law of gravitation was the discovery of Neptune. As you know, the discrepancy in the motion of planet Uranus was explained by Adams and Leverrier in terms of a extra planet which should be in existence, which was subsequently discovered and called Neptune. Now, here are the observational records of actually finding Neptune, and the prediction was made by Leverrier and conveyed to the observatory in Berlin, and they found it in that particular way. So, these are excellent examples why a speculation, if it is along the right direction, can lead to factual confirmation. But at the same time, I want to draw your attention that two speculations together do not take the place of a fact. That is, sometimes you are given one speculation and then another speculation to back up the first speculation, but these together do not make a fact. And I want to refer back to the example of counter earth, that counter earth was invented in order to explain one speculation. And I will come back to this in the context of my main theme of today, how this is happening. Another example in astronomy where speculation is backed by facts is the application of laws of physics to stars, to the interiors of stars. Now, here you have a diagram which astronomers know as the HR diagram, which is the Hertzsprung-Russell diagram. But what it describes is on the vertical axis you have the luminosity, how bright the star is plotted here, and on the x axis, horizontal axis, you plot the temperature of the surface temperature of the star. So, and the temperature is decreasing this way, luminosity is increasing this way. And you see all these points which correspond to actual stars which have been observed. Now, what you find is this line going through. This is the mathematically computed line, which is based on Eddington's kind of calculation and application to stars of different masses. So, for each mass you will get a point on this line, and what you see is that this particular trend is very well explained by the observations. So, here you see the speculation or the belief that laboratory physics can be applied to stellar environment is borne out by by facts. You see some stars here. You can ask, what about these? So, these are red giant stars, which are very large, but low temperature stars, and they can be explained by going further in the evolution of these stars. And when you do that, you find that these stars can also be explained by a theoretical line very well. So, you have here a situation where not only you have application of the law, but you have what scientists always like to have, a repeated experiment. That theory should not be applied only once to a particular case, but it should be repeatable under different conditions, as laboratory physicists like to vary the parameters of the experimental setup. In the same way, astronomer is varying the mass of the star here, and he is getting the right answers. So, with this kind of background, I now come to standard cosmology, that is the standard Big Bang cosmology. In 1922-24, Alexander Friedman produced mathematical models of the expanding universe by solving Einstein's field equations. Now, what is expanding universe? If you take galaxies of the kind I described earlier, like Andromeda, you find normally the distances between galaxies are increasing systematically. So, the whole universe in which these galaxies are located is, as it were, expanding. Now, you can associate a scale which will denote this expansion. So, any galaxies you can take the distance between two galaxies, and that is increasing with time. Now, what Friedman's models do are they are mathematical solutions of Einstein's field equations, and they tell you how the expanding universe kind of situation arises. Different models give different types of expansion. Now, in 1929, Edwin Hubble found the so called MZ relation, that is the redshift magnitude relation. Now, I will briefly explain what this is. On this side, you have different galaxies which you see at different distances. So, as you go down, you are looking at fainter and more distant galaxies. So, they are looking smaller and fainter, and this is nearer one. On the right hand side here, you have the spectrum taken of these galaxies, the light of the galaxy. And in these spectra, you have certain absorption lines, dark lines, which you can just about make out, and these dark lines are moving as you go down in this sequence. They are moving toward more and more towards the right. So, these arrows are showing how the lines have shifted. So, the standard way of looking at a spectrum is to say, on this side there is the blue end, on this side there is the red end. It is like these 7 colors which you get when you hold a prism in sunlight, you get these 7 colors. So, because the lines are shifting to the red end, this is called redshift. So, what Hubble proved was that as you look at more and more distant galaxies, the redshift increases, and this was the kind of result which is explained only with the help of Friedman's expanding universe in the most simplified way. There are other explanations of redshift, but what you have to notice that Friedman had 5 to 7 years earlier made a prediction, and that has been verified. So, in that sense, one can say that this was a good test of a expanding universe idea. Now, Einstein himself was not very happy to start with the expanding universe idea. This was in the at the time when Friedman got his solutions, he sent them to Einstein for his comment, but Einstein did not, there is no record of what Einstein said, but presumably he was not very impressed, because the belief was at the time that the universe is static. In 1917, Einstein himself had obtained a model of the universe which he wanted it to be static. Now, he could not get a static model from his field equations, because when he tried to put the solution, it just would not satisfy it. So, either he could have said that the universe is not static and my equations are right, or he could have said that the equations are incomplete and the universe is static. So, he preferred the second alternative, and he said that we will add a cosmological term to the equations, so that he will get a static solution. So, this is the static solution, in which the as the time goes in this way, there is no increase or decrease in the size of the universe. But when in 1929 Hubble found proof that the universe is not static, then gradually Einstein lost his interest in the cosmological term and he gave it up. But there were other people like as I said here, Einstein gave it up, but other people who said, why not look at other solutions and enlarge the parameter space of the cosmological models. So, this idea has been there and one way of testing this, whether this cosmological term is there or not, is to ask whether the universe is decelerating. That is, when you have the expansion of the universe, is the expansion at a steady rate, or is it faster, getting faster with time, or is it getting slower with time? So, is it accelerating or is it decelerating? So, this question astronomers have been asking, and one can define by two parameters. One is called the Hubble constant, which measures the rate of expansion of the universe, and the second time derivative of the scale factor is measured by the parameter q, which there is a minus sign is attached here. So, if q is positive, the universe is decelerating. So, the idea that astronomers had was to measure q by going into larger and larger distances. So, the Big Bang models which were in favor during the period 1960 to 1980 all had q greater than 0. That means, the universe was decelerating, and all the observations were based on this redshift magnitude relation of the kind Hubble had got, but going to larger and larger distances, because if you want to know how the expansion is, whether it is getting faster or slower, you have to measure over larger time span. And that is why this was when the q was measured, people always found q greater than 0, and the only model which gave a negative q, which was an accelerating universe, was the steady state model, which was not a Big Bang model, and so it was always singled out as a wrong model, because it gives a decelerating accelerating universe. So, I would like to come back to this point in the modern context, because I am talking here of 1960s to 1980, when this was the prevalent view. So, I will come back to this, but let me now go further into the cosmological model, and the next important speculation was made by George Gamow, that if you take the expanding universe and look at its past, the universe must have been smaller, and when it was smaller, it must have been denser. It will be more packed with matter than it is today. So, not only denser, then it will also be very hot. So, as you go closer and closer to the Big Bang, that is the time from where the whole universe exploded, that was the Friedman model's prediction, then you find that you go to a state where the temperature was so high that primordial nucleosynthesis could take place, which means nuclei of atoms, smaller atoms could come together and bigger atoms could be made. So, this was the idea that Gamow had, that one could build up from simple neutrons and protons heavier nuclei, and he succeeded. And when we look at the calculation in modern context, we find that he succeeded so far as light nuclei are concerned, deuterium, helium, lithium, beryllium, boron. These are generally of the right order of magnitude. This is a technical slide I just put in to show that people have been comparing these predictions with observations and finding them to be of the right kind. But heavier nuclei like carbon, nitrogen, oxygen, or copper, iron, or heavier ones, they cannot be made in the early universe. This is now well accepted. They have to be made inside stars only. So, Gamow's speculation was partly correct, partly it turned out to be unsuccessful. But there was another prediction made by two of Gamow's younger colleagues, Ralph Alpher and Robert Herman, that if the universe was very hot in the very early stages, then there was lot of radiation around which was very hot, and that radiation should be around today at a very much lower temperature, and they made a guess that the temperature would be 5 Kelvin. Well, there are some technical issues which I will not go into, but this is the present measurement of this radiation, and if you assume the black body, which is the radiation produced in a universe which was very tightly packed, then that black body radiation curve very nicely fits these observations which are shown by squares. So, these squares are error bars, and you see the fit is extremely good. The temperature is around 3 degrees, not 5 degrees, but very close to 3 degrees. So, one can say that this was another successful prediction made by the Big Bang model. Now, when we look at this early universe hypothesis of Gamow and his colleagues, we can see that the physical basis of this is very secure for the following reason. The physics that it uses, the nuclear physics, the thermodynamics, and the expansion of the universe, the statistical mechanics, all this is well tested in the laboratory, and that is what Gamow was using. So, one can say that the physical base of this was very sound. But the astronomical base is not secure, and I will explain why the astronomical base is not so secure. When one looks at direct observations with the telescope, one looks at galaxies, quasars, and so on, and one finds that the farthest you can go is of the order of redshift of 6. That is, we are able to look up to this. Now, the Big Bang cosmology says that the universe is opaque beyond redshift of 1000. You can make up a kind of picture in your mind that redshift is a measure of distance from us, and the further you are looking, the further back in time you are seeing the universe, because light takes time to come to us. So, the epoch when the redshift was 1000 was much earlier in the universe than the epoch when the redshift is 6. So, what is happening is the following that this result which the Big Bang cosmology comes up with, that the universe is opaque beyond the redshift of 1000, means if you want to set up a telescope to look into the past history of the universe, you cannot go beyond redshift of 1000, because you will hit a blank screen or a screen which you cannot penetrate. Now, Gamow's calculation of the early hot universe go to redshift as high as 10 to the power 9, that is a billion. So, Gamow was talking about a universe which was certainly not visible or observable from our present epoch. So, it is some kind of extrapolation expecting that this is how it is like. So, to give you an analogy, supposing this is a stage and you have a screen which is curtain which covers the whole stage, and you are looking on from that side and something is happening on the stage, but you cannot see because the screen is there, the curtain is there. So, what you do is you make guesswork what is happening there, and maybe there is some fight going on and some missile comes out of the screen and you say okay, there is a fight going on, but you cannot directly see it. So, in the same way what astronomers do and what Gamma was doing was to make assumptions that this is what was going on, and then you say that the result of that would be to see something today. So, it is a kind of indirect way of checking. So, it is not a direct observation of the universe. So, what one says that when you look at nuclear abundances today and the microwave background radiation today, what you are doing is trying to guess what happened behind that curtain and then saying this is what happened and that is why you are seeing what you see today. So, one has to be aware that it is not a direct observation that people should be making. Now, other thing is that the universe is a one and only system. You cannot have repeated experiments. You cannot say I want to have a second big bang and see what happens and I will test what you have said so far. So, it is therefore an event which occurred once and only and you are trying to interpret it. So, it is not a repeated experiment or repeatable experiment as science requires. Now, the subject which has grown recently out of this extrapolation of early very high energy state of matter, particles were very hot, very energetic and very early in the universe. This subject is called astroparticle physics. That is, you put in some inputs from high energy physics and some inputs from cosmology, and then because these are two different disciplines, they should be brought together and we can then try to understand what the early universe was like. Now, when you do this kind of study, what happens is the following. Here you see a photograph of a high energy particle accelerator like in CERN or Fermilab. So, here you find particles circulating at tremendous speeds, and high energy physicists learn how the particles interact by their collisions and so on at such high energies. But when they want to study what is their ultimate goal, this what they call grand unification of all fundamental interactions, they require energies much higher than what these particle accelerators can generate. And so, they say the only place we can find such energies is in the Big Bang. If we go sufficiently close to the Big Bang, we will find particles moving very fast, and therefore, we can study whether our particle physics theories work. So, what the particle physicist thinks when he goes into this partnership with the astroparticle physics with cosmologists, that since the Big Bang is a well established theory and secure as a theory of cosmology, let me try my speculations of very high energy particle physics in this background. So, he assumes that the Big Bang is well established and he will apply particle physics at very high energies. On the other hand, what the Big Bang cosmologist thinks is that since particle physicists know what they are talking about, let me apply their theories to test my speculations of the very early universe. So, he believes that things are very well established or known, understood in high energy particle physics, and we are using those to understand what the Big Bang cosmology is like. So, you have two people meeting, each thinking the other knows everything about his subject, but actually particle physicist does not have any experimental setup to test his grand unified theories, and cosmologist does not have any way of observing that very early universe. So, the fact is that both sides are using speculations. So, I now come to the situation where two speculations are brought together to persuade you that you are looking at a factually established paradigm. So, one such example is found in the notion of inflation. This rests on the idea that when the grand unification took place, which is the energy of this order, and let me again emphasize this energy per particle, whatever this number is at least 1,000 billion times the energy which particle physicists can measure in their Fermi lab or CERN type experiments. So, you are making a 12 to 13 orders of magnitude extrapolation when you go to this, and the universe, when it had this kind of energy, was only 10 to the minus 36 seconds old. Now, what does that mean? It mathematically you can of course define any number, but what does it mean? So, you take a million, you divide 1 by a million, go on dividing by a million 6 times. So, you will get a very short time scale. Now, a physicist should have an operation which will tell you how to measure such a time, but we do not have any any way of measuring this time, but the statement is made that at this time the universe had this kind of energy per particle. So, and at that time when some things happen, the universe suddenly started expanding very rapidly, and it lasted for a short while, and that is called inflation. The word inflation was used by cosmologists to not in the way economists use them, but a sudden rapid expansion. It is an exponential expansion, that is like compound interest grows very rapidly instead of simple interest. So, the universe suddenly expands, and that is called inflation, and it arises by extrapolating your physics to these kind of energies. So, I can ask, is the physics behind inflation well and independently tested? And the answer is no. There is no independent test of this, because energies of that order have not been obtained. Then, has inflation been directly observed? You can go to the other question, whether it is possible for astronomer to look back far enough in time, but as you know, you are already encountered, you have encountered the thick curtain. So, it is happening behind the curtain. So, the answer is no. Then you go to the third question, is this a repeatable and observable phenomenon, that can inflation occur many times and you can observe, just as you can observe different stars. So, the answer is no, and so there are no to all these three questions. So, then can two speculations together add up to a fact? We come back to the original thing which I ask you to remember what happened with counter earth. So, I will give you an excellent example of how this was done in astroparticle physics. There were two speculations. First was that if you have grand unified theories, that is when particle physicists were able to combine all the interactions into one, the conclusion was that there would be magnetic monopoles around, and you cannot avoid them. Normally, when you take a magnet, bar magnet, it has south pole and north pole, but you can, if you want to divide and get one pole by itself, you cannot do it, because you find there are two poles. So, magnetic monopoles normally do not exist in nature, but if you had grand unified theories working at certain time, then at that time magnetic monopoles would exist. Not only that, they would continue to exist today. So, this conclusion was drawn in the 1980s, and as cosmologists were very worried as to what will happen to those magnetic monopoles today, because there will be a lot of monopoles around, too many to be explained by observations. So, at that time inflation people came in and they said, because of inflation you can blow them away. So, there will not be any magnetic monopoles left. So, you have two speculations, one is grand unified theories, the other is inflation. And what you find is couple of statements which you are asked to believe. A grand unified theory operated in the early epochs and inflation took place in the very early epochs. Both these statements have no independent factual support, but what do you claim? Why do you see this, these two statements to be right? Because you do not find any magnetic monopoles. So, a null observation, you are not seeing something and therefore, you are deducing two conclusions, and this was very strongly motivated, this particular argument very strongly motivated belief in inflation. So, now I very briefly come to this standard Big Bang scenario and tell you what is supposed to be happening. You had a Big Bang, then during this early stage, when we are talking of a time scale 10 to the power minus 43 seconds, even shorter than 10 to the minus 36 seconds I had mentioned. During this period, gravity was controlled by quantum mechanical laws. So, instead of classical gravity, you have quantum gravity, and the result of this is supposed to give these tiny quantum fluctuations. Then you put in inflation, which grows these fluctuations in a certain way, and then you encounter the screen and you come out of the screen and you can observe this is the microwave background screen, and then you begin to see galaxies, etc., and whatever you see today is this. So, your whole idea is to form galaxies from this through this kind of sequence of events, of which you are able to see the local neighborhood, you can see the galaxies, but beyond that you cannot see anything. At least you have not seen anything today from here onwards back. Whatever you claim to have seen is a guesswork, that if you had something happening here, then this is what will happen and that is what we are seeing. So, there is no direct observation of any of these things that happened. And since I talked about epicycles, I would like to show how the epicycles have built up around the standard Big Bang. First, they found that there was the Friedman model. This is the first epicycle, first circle. Then people put in the lambda term, the cosmological constant which Einstein had introduced, that came in to give you more models. Then people brought in n body simulations where equations became nonlinear, you could not handle them. So, people had different codes, but we still do not know whether there is a unique way of dealing with these matters. Then dark matter was introduced, and I will come to this next. Then biasing, how the dark matter is distributed with respect to visible matter. I will come to that. This is an extra assumption. Then inflation was put in, and people still do not know which particular model of inflation is the valid one. And then you have the quantum fluctuations. So, you have this kind of epicyclic theory of Big Bang today. So, I come now to dark matter, and I want to liken it to the story you may have read, Emperor's New Clothes, where the emperor was very fond of trying new dresses, and some con men came and said, we will give you the best dress, and only the people who have not sinned will be able to see it, and the dress they gave him was no dress. So, everybody had to pretend that they were seeing dress on the emperor. So, like that I will now come to the dark matter. First of all, let me state that there is some very good evidence for dark matter, and one of the evidence is in this picture. Again, I will not go into technical details, but what happens is the following. Here you are measuring the velocity of rotation of clouds of neutral hydrogen going around galaxies, and the further you go the gravitational field of the galaxy will be weaker and the clouds will start moving slower and slower. To give you an analogy, you take planets going around the sun. The sun has a given mass, but as you go further and further out, the planetary speed goes on decreasing. So, Pluto is moving much more slowly than the Earth, and we are moving much more slowly than Mercury. So, this is what law of gravitation tells you. Now, when you do this, you find these velocities are not going down, even if you go further from the galaxy. So, why this is happening? Is the law of gravity wrong, or is the law of motion wrong? Well, maybe it could be wrong, but if you assume that they both are right, then the assumption, then the conclusion is that even though you see the galaxy as shining, as a kind of cloud, shining cloud, beyond a certain distance, there is more matter in the galaxy which is dark, which cannot be seen. So, you argue that all these M31, M101, our galaxy M81, they all have dark matter. Similarly, this is a cluster of galaxies. So, many galaxies in this picture, and they are moving very rapidly. Now, if this cluster is in equilibrium, then there should be a certain standard speed, that average speed that these galaxies should have. What is found is that the speed observed is much more than that average speed, which means again that there is lot more matter turning them round and we cannot see it. So, you have another example of dark matter which you cannot see, but whose evidence is still there. So, here so far there is no analogy with emperor's new clothes. Dark matter is there, then it's ordinary so long as you say that this dark matter is ordinary matter. But if all this dark matter were ordinary matter, Big Bang cosmology would be in trouble, because deuterium production that was supposed to have been done in the very early history of the universe would be all washed out. There would not be any deuterium left. So, people say, and this has gradually, although the dark matter was becoming accepted in 1975, in the later years, that is in more recent times, Big Bang cosmologists, if you ask them what is the dark matter made of, so they will say they are made of strange particles, and they are WIMPs, massive neutrinos, supersymmetric particles and so on, none of which have been observed in the laboratory. Now, why do you go for this? Why not ordinary neutrons, protons? Because if it were ordinary neutrons, protons of which we are made or of which stars are made, then you will find that Big Bang cosmology gets into trouble. There are many aspects which do not work out. So, you have to invent non-baryonic dark matter. This is the word used for this, that is matter which is strange, which is not ordinary, and that matter has to be there. So, if dark matter turned out to be wholly baryonic, it will pose problems for Big Bang. There will be too little primordial deuterium. The formation of large scale structures would produce very big fluctuations in the microwave background, which are not observed. And for these reasons, the Big Bang cosmologists automatically assume that ordinary matter is ruled out, and you are asked to believe in these matter. And these are what I call emperor's new clothes, because there is no laboratory evidence for them. So, this is my grouse against non-baryonic dark matter. Then since 1999, another aspect came into it. People began to suddenly talk about dark energy. Now, what is dark energy? This is not dark matter, but dark energy. Now, the dark energy comes in the following way. When I described to you the 1960s, 1980s experiment of looking at the Hubble diagram, looking at redshift and magnitude to larger and larger distances, which led to the conclusion that the universe is decelerating. That was the conclusion in the 1960s to 80s. But when in 1999 onwards, people began to look at some very distant galaxies which had supernovae, which are exploding stars, they found that these distant supernovae were much dimmer. They did not appear as bright as expected from a standard decelerating universe. And the only way to accommodate them was to assume that the universe is accelerating. And the observations of cosmic microwave background, they also suggested that you need to have this cosmological constant which produces acceleration. So, the situation is and the structure formation also requires now to have a cosmological constant. So, let me draw a balance sheet for lambda, the Einstein's cosmological constant. So, in the previous studies, the redshift magnitude relation revealed that there are several practical pitfalls in the claims to measure the deceleration and acceleration of the universe. During 1960 to 80, there was, as I mentioned, a big effort to measure the deceleration of the universe. But towards the end, astronomers began to realize that the observational errors or uncontrolled errors are too many, and you cannot make a definitive statement. And therefore, those efforts which were carried out in the 60s and 80s were not repeated subsequently. But today, people again seem to be very much carried away by the supernova test, without realizing that similar experimental errors might still be around. And though rejected by Einstein and most cosmologists from time to time, the lambda term keeps coming back whenever the theoreticians find the observations too difficult to explain. And if you look at history of cosmology in the 1930s, then 1970s, and then now, people have been saying now there should be a cosmological constant. And what happens is that whenever there is a realization that something new has to be explained, this constant is taken out of the mothballs and put out. When people find the observations are not very important, then they put it back again. So, what are the reasons why lambda is required? One is it solves the age problem. Now, if you take Big Bang universe, you can calculate the age of the universe, that is the time taken from Big Bang to the present epoch, and that time would depend on what kind of model you are using, mathematical model. On the other hand, you can compare that age with the oldest stars you find around you or in your galaxy. So, it turns out that you need something like 14 billion years, 14 giga years to explain, that is, universe must be 14 giga years old. Now, if you take that kind of universe and you do not have a lambda, then you find the universe is too young, it cannot accommodate such old galaxy. It is like saying if the universe is the father of everything, that father is younger than the son, that kind of thing. So, the age problem is solved if you are allowed to have lambda. Similarly, the fluctuations of radiation background and as well as the dimming of distant supernovae can be explained by having lambda. And people also like to say that this lambda term came out of inflation, which Einstein did not have at his time, but inflation is supposed to have generated the lambda term. So, this is one plus point on inflation. Unfortunately, there are problems also. If you assume that inflation gives rise to a cosmological constant, how does it compare with the cosmological constant you need today? It is like saying a theory makes a prediction. If it is wrong by 10%, 20%, you say, okay, there is some possibility of adjusting it. But this inflation cosmological constant is 10 to the power 108 times what you need. So, I do not see this as a successful prediction of inflation if you are coming out with such a wrong answer. And how is dark energy typified by lambda related to the rest of forces in nature? That is, how does lambda find a place in the overall grand unification scheme? That also is not understandable. So, the general comments that I want to make to summarize is that the studies of the very early universe are highly speculative, both in terms of astronomy and particle physics. They describe a scenario that is not expected to repeat. Then normal physics, that is statistical mechanics and extrapolated flat space time, etc., cannot be used in describing these scenarios. Direct observations of the universe extend to densities of matter about 200 times the present value, if you go to redshift of 5 or 6. But the extrapolations are carried out to a density 10 to the power 87 times what is observed. Now, when astronomers look at neutron stars, they find very high densities, and that is of the order of 10 to the power 15 times the density of water. Now, it may sound very high, but that is the kind of density in the nucleus. But here it is much more than that. And when astronomers were looking at neutron stars, they were very careful in understanding the equation of state, how matter behaves at such high densities. But cosmologists never seem to worry about what state of matter it is which has that kind of density. So, I come to my original question, is cosmology a science? And my answer in a very long sentence is the following, that although remarkable strides have been made both in theory and experiment in physics, and telescopes of various kinds have enlarged man's capacity to observe the universe, by the normal criteria of close interaction between theory and observation, cosmology as it is practiced today has far too large a speculative element to qualify for the science, for the title of a scientific discipline. So, this is my conclusion, and I want to go to show you couple of cartoons which I received by post about 20 years ago from Grote Reber, who was also a pioneer radio astronomer. During the Second World War, he was starting radio astronomy observations. So, he was against Big Bang. So, when he learnt about my doubts about Big Bang, he said, you may like to see these two cartoons. So, this is the first part of this. The world will end with a Big Bang, that is what he says. So, the second part says that there are some fools who say that is the way it started. So, I think I will finish here. Thank you. So that.